Hello everyone, this is Mingliang. My talk is titled Target Netgrams, an Annulus-constrained stress model for radial graph visualization. This is our agenda. Graphs are very common data structures on the internet, such as social networks. In social network, users often care about an important node and its neighbors, and many methods have been proposed to explore such subgraphs centered on important nodes. A popular method to visualize such subgraphs is radial layout, which positions nodes on circular lines to show the hierarchy of the subgraph, but it often fails to show the structures of clusters. Another method, flexible radial layout, tries to preserve cluster structures but is limited to the layout space, resulting in the fragmentation of clusters. Moreover, both methods suffer from significant overlap. To solve these issues, we propose target netgram that position nodes onto the annulus between adjacent circles rather than on circular lines, which allows to maintain clusters and neighborhood structures while reducing overlap better than previous methods. Now I'll briefly introduce some related works. For subgraphs with a central node, the most common representation is radial layout. It can accurately express the hierarchical relationship between the nodes to the center, and the nodes are uniformly distributed, but the relationship between nodes will be seriously damaged. Another common layout method, stress model, maintains relationships between nodes, but node-to-center hierarchies will not be maintained. A similar method, flexible radial layout, considers the node distance relationship by combining radial layout with stress model. However, the readability of this method is still unsatisfying because of the limited layout space on concentric circles. To improve the readability of radial visualizations, we use a design called target sociograms. This design arranges nodes in a range between concentric circles, creating more space and improve the readability. Before, there was no automatic way to generate such visualizations, so users had to manually create them through interaction. So here our approach will fill this blank. The design requirements of our method is summarized as follows. Firstly, preserve hierarchical structures by satisfying the radial level constraint. Secondly, preserve neighborhood structure for easy exploration of local graph topology. Lastly, ensure readability by evenly distributing nodes within concentric circles. Based on these three design requirements, we propose a three-term optimization equation as our model, which we call it target netgrams. The three terms in this model are the angular term, the stress term, and the level constraint. The model works as follows. We first ensure the uniform distribution of nodes by mapping them uniformly onto the circles of the corresponding hierarchy through the angular term. Then we satisfy the structural and hierarchical preservation requirements through the stress term and the level constraint. Finally, we get the result by solving the optimization with hard constraints. The algorithm of solving optimization with constraints works as follows. In the process of solving the optimization equations, we set the upper and the lower bound constraints to limit the node positions until all nodes satisfy the constraints. Along with this framework, we design several user constraints and tools to help user explore the subgraph. The first one is the parent-child preservation constraint. It helps the user to reduce unexpected long parent-child nodes and node overlap across clusters while keeping the hierarchy. Attribute-based clusters allow users to select and group nodes according to their node attributes. Structure-aware radii creates the necessary space for flexible interaction that are needed when exploring graph structures. Users can further magnify interesting levels and attach attribute-based statistical charts to the nodes. When a new center is selected, a two-stage animation with uniform node velocity is performed to allow viewer following the transition easily. Now I will show the benefit of our method by evaluation. In the quantitative study, we selected 4 social networks, and in each network, we chose 100 nodes as the center to generate subgraphs for testing. Then we selected 3 structural preservation metrics and 3 readability metrics for test. We first compared our method with the 3 most important related works on structural preservation. In summary, target Netgrams performs better than most of the baselines on these 3 metrics. Although stress error and neighborhood preservation degrees of target Netgrams are slightly worse than that of the stress model, our method is able to maintain the radial level constraint. Then we compared our method with the 3 related works on readability. Target Netgram performs slightly worse than stress model, but performs slightly better than the radial-based methods. To further evaluate our method in terms of human perception, we designed a user study. We let the user find the maximum degree of nodes in the certain level of a subgraph. This task tests the performance of this method on both level preservation and readability, which is well suited for demonstrating the effectiveness of our method. For result, we found that our method is significantly better in terms of task completion accuracy and slightly better in terms of task completion time compared to other methods. Lastly, we provide a case study. Here we apply target netgrams on a collaboration graph extracted from the DBLP dataset. Users are able to fine-tune a layout to display more relationships according to node attributes during interaction. Target netgram will not distort the local structure of a graph. This demonstrates the effectiveness of our method. In conclusion, we propose an Annulus-constrained stress model that aims to satisfy radial level constraints while depicting graph clusters, neighborhood structures, and reducing node-to-node, node-to-edge overlaps as much as possible. Secondly, we provide various constraints and rich interaction methods for exploring node edges and levels of interest. Lastly, we demonstrate the effectiveness of our method through a quantitative evaluation, a user study, and a case study. More details can be found from our website, and thanks for your attention.